So today we're really excited to have Alessio Roccon as our speaker, who is currently an assistant professor at the University of Udine in Italy. Previously, he was a postdoc at the same institution and also at the Institute of Fluid Mechanics and Heat Transfer at TU Wien. He received his PhD in environmental and engineering science, also from the University of Udine. And his research involves fundamental problems in fluid mechanics, particularly focusing on interactions between turbulent flows and deformable interfaces. So he has expertise and research experience in high performance computation of turbulent flows with interfaces and in phase field modeling. And today we're really looking forward to hearing about some of his work on phase field modeling of heat and mass transfer phenomena. So with that, I'll turn it over to Alessio.
Yeah, thank you, Andrea, for the kind introduction. Good morning, or good evening, depending on if you are in Europe or US. So my name is Alessio Roccon, and I'm assistant professor at the University of Udine, and also have the affiliation with the TU Wien Institute of Fluid Mechanics and Heat Transfer. So in today's talk, we're going to go through on the phase field modeling of heat and mass transfer phenomena in turbulent flows. So first, just to give you an overview, where is Udine? Udine is located in the northeast part of Italy. We have different buildings, like you can see here, let's say the literature building, and also the engineering building, which is located a bit outside of the city center. Now, back to science. So in today's talk, we're going to go through three main topics. So first, a bit of motivation and introduction on the phase field modeling of and why we want to do this kind of simulation of multiphase turbulence. Then the first topic will be heat transfer in drop-laden turbulence. And finally, we're going to move to an extension of previous work to boiling heat transfer modeled with a phase field approach. So why you want to do this kind of simulation in which we try to resolve all these kind of bubbles and turbulence interaction? Because this kind of flow are very important, like in, just to give you three example, in nuclear energy or in electronic device in which we use heat pipes to cool GPUs or CPUs. And also on breaking waves in which we have mass transfer phenomena, and also the interaction of bubbles and drops with these waves, and also this kind of drops and bubble can also modify the heat mass transfer across the oceanic surface. And this has strong implication, like for instance, in climate change or climate change mitigation policies. Now we want to have space and time resolving information on this type of flow to optimize or to better understand and model this kind of phenomena in all these different type of application. Now the question is, how can we simulate these systems? Indeed, if we consider just multiphase turbulence, so drops or bubbles immersed in a flow, we already have three main salient features. The first one, we have drops that can have very complex shape, like the one that you can see in red here. So we have very strong deformation and very particular, very peculiar shape of the drops. We can also have two drops that get together and they merge. And in this case, we have a topological change of the interface, and we have a change in the surface to volume ratio. And finally, we can also have, like you can see here in green, like thin ligaments that are produced by the breakage of drops. And also these ligaments have a very peculiar shape, and they have a very high surface to volume ratio. So they are very prone to exchange mass and heat with the carrier flow. Now, on top of this, which is just the multiphase turbulence, we have heat and mass transfer. Heat and mass transfer can be strongly influenced by the shape, and also in some cases we have a scalar like heat or mass that can be confined in just one phase. Like if we have surfactant, they can move maybe in one phase but not go into the vapor phase or in the air phase. Topological changes can also change the mixing. For instance, if we have two small drops that merge together, then we're going to have a modification of the surface to volume ratio, so a larger relaxation time, and the drop will take much more time to release heat and mass to the carrier phase, or the opposite if we want the drop or bubble to absorb something from the carrier flow. So we want to try to also model heat and mass transfer in this kind of flows. Now, this kind of flows, just speaking about multiphase turbulence for the moment, are very complex. Indeed, we have a large scale separation between all the different phenomena that are relevant to this type of flow. We have the macroscopic hydrodynamic scales, which are the larger one and can control the motion of these drops. But then if we consider, for instance, the coalition between the two interfaces, so when two interfaces are very close one to the other, we don't only need to solve the smallest turbulent scale, which is the Kolmogorov scale, but we need to further go down to the atomistic scale of the system to also solve the interaction between, like, for instance, the surfactant molecules that we can find at the interfaces. Indeed, it's only at the atomistic scale of the interfaces that we are able to model the correct interaction between two close interfaces. So we have a wide range of scale that we cannot directly solve from first principle, also because the continuum hypothesis break down at a certain point. So it's very difficult to resolve all the scale, also from a computational point of view, because we don't have enough power, computational power in current HPC machine. So we need to, let's say, focus on a certain range of scale. In this case, we focus on the macroscopic hydrodynamic scale, and we perform something that is called interface resolved simulation. We have also other methods depending on which scale we want to solve. So today's focus is on interface resolved simulation. So we solve a range of scale that is close to the macroscopic hydrodynamic scale and are close to the drop size that we can model. And we try to, let's say, we are not solving the smaller, let's say, molecular dynamic scale or other type of scale for the drop and the flow. Like, for instance, in the Lagrangian particle approach, we assume that the drop or bubble are much smaller than the smallest Kolmogorov scale, and we can basically model them with a different type of approach. Here we focus on interface resolved simulation. So the interface of the drop, so the drop size and the turbulent structure have more or less the same size. Now we want to describe the interface. So the type of flows that we have is the one that we have on the left here. It's a droplet flows. And usually the flow is described with a grid-based description. So we have a grid with some nodes and with the velocity at these points. Now we also need to describe the interface. And here we have two different possibilities. The first one is interface tracking. So we put some marker on top of the interface and we follow the motion of this marker point. And this will give us the motion of the interface. Another possibility is the interface capturing family method, in which we define a color function that is 0 inside, let's say, the drop, or 1 outside the drop. And with an advection, the diffusion equation for this color function, we basically advect the interface, which can be conveniently defined as the ISO level of this color function, like the ISO level 0 or 0.5 usually. Now, the different approaches that are available in these two main families for the interface tracking, the most popular is the front capturing, while for the interface capturing, we have the volume of fluid, which is the oldest one, in which we have a color function that is 0 outside the drop and 1 inside. The level set, in which we can transport a certain property of in this case, the distance function, or the approach that we're going to use in this talk, that is the phase field model, in which we have an advection diffusion equation, and we have a thin transition layer between the two different phases. So it's a kind of diffuse approach to model the interface. Now, in the phase field method framework, we have a marker function, so the phase field variable, and we have two types of main methodologies that we can use. The first one is the candidate equation, that is a four-order equation that we solve to obtain the evolution of the phase field function, or the conservative Allen-Kahn, which is a bit newer approach, which is a simpler equation that we can also use to get the time evolution of the phase field variable. So the main feature is that we have a thin transition layer between the two phases, so we don't need very complex method to reconstruct the interface, like in the volume of fluid, in which we need to reconstruct the interface normal or do other schemes. But with very simple scheme, we are able to advect and diffuse this equation and to transport the interface properties across in the computational domain. Now we can think of coupling the phase field method with a direct numerical simulation of the Navier-Stokes equation. And what we get is this kind of system of equation. So we describe the flow coupling the mass conservation equation with the Navier-Stokes equation, in which we have the last term here at the right-hand side represent the surface tension forces. So the amount of energy that is exchanged via momentum by the surface tension forces. So the first two equations, mass conservation and Navier-Stokes, will give us the flow field in the entire domain. So it's a one fluid approach. While the second one equation, which is in this case the Caniglia equation, will give us a phase field variable that is 0 or 1, and that will give us where we are inside one drop, where inside the drop phase, and where we are outside the drop phase, so we are in the carrier phase. So this is the building block for our solver to describe multiphase turbulence. We have all the fundamental ingredients to describe multiphase turbulence. So we have the surface tension action, the phase field, so where the interface is located, and the flow field in the two phases. Now, this is the building block that we're going to use in the next two topics. The first one is heat transfer in droplet and turbulence. So we want to understand how a swarm of hot drops release the heat through the interface and to the carrier phase. So in particular, drop can have different dynamics, like they can deform, or they can also coalesce, or they can also break into different smaller drops. We want to try to quantify the effect of this phenomena, so deformation, coalescence, and breakage, on the heat transfer, if they enhance or not enhance the heat transfer from the drop phase that is warmer to the carrier phase that is usually colder. For this initial study, we do some assumptions, which are no thermal dissipation, a small temperature difference, so we can assume that the viscosity and density of the two phases are constant and do not change with temperature. No buoyancy and no thermocapillary forces. Indeed also surface tension can change depending on the temperature. And for the moment, we neglect the phase change, so we assume that there is no evaporation, boiling, or condensation across the interface. Now we start again from the building block, which are the flow and interface description, so continuity and Navier-Stokes equation, plus the surface tension term, the Caniglia equation to describe the evolution of the phase field variable, and we add an additional equation, which is the energy equation, that describe the temperature now also in the two phases. So the last equation will give us the temperature evolution in the entire domain, so inside the drop phase and inside the carrier phase. Here we have three main parameters. One is the Reynolds tau, which is the shear Reynolds number in this case, which is a parameter that quantifies the amount of turbulence that we have in our channel. The Weber number, which is the ratio between the surface tension, the inertial forces, and the surface tension forces. So higher is the Weber number, more deformable is our interface, so it's more prone to breakup. And the last parameter is the Prandtl number, which is the ratio between the momentum diffusivity, so mu over rho, against the thermal diffusivity alpha. So it's kappa over rho Cp. Now we solve this equation with our in-house pseudo-spectral solver, which is called Flow36, which is now open source. So we use a channel flow in which two directions are periodic, and in one direction we have two walls, so it's two parallel plates. We use a wall normal velocity formulation for the Navier-Stokes equation, so we do not solve for u, v, and w, but instead for the omega z, so the vorticity along the z direction, and the wall normal velocity, plus the definition of vorticity. It's a pseudo-spectral method, so we, instead of solving the physical space, we transform everything in the spectral space, in which Fourier are used along the periodic direction, while Chebyshev polynomial are used along the wall normal direction. And the Caniglia equation, which is in this case a four-order equation, is split in two second-order equations. So by solving this system of equation, we get, starting from, let's say, the velocity and the phase field variable at time step n, the new solution at the time step n+1. The code is a massively parallelized code. So we have a 2D domain decomposition. So we split our domain in different pencil, and we use MPI to perform the communication among different, let's say, among the different MPI tasks. We use the FFTW library to run on CPU cluster, while we can also use GPU acceleration, like for instance on Leonardo, in which we have 100 GPUs available. We can use OpenSSD directive and CUDA Fortran instruction to run also on GPU cluster, in which we're going to use the QFFT library to perform the transform in this type of on the GPUs instead of using the CPU. Now, the system that we consider for this first type of analysis is a channel flow, so the flow between two parallel plates. We start from a single phase turbulent channel flow, so the classical single phase turbulence. And we start from 256 drops divided in two arrays, so one on top of the other. And the drops are initially hotter than the carrier phase, and the two walls are adiabatic. So basically the system is closed, and there is no exchange of heat from the walls to the outside. We consider a Weber number equal to 3, which corresponds to a oil and water emulsion, and it's characterized by a high deformability, so drops are very likely to break and undergo breakage occlusions events. And the main parameter that we investigate is the Prandtl number, so the ratio between the momentum diffusivity and the thermal diffusivity. As we increase the Prandtl number, we also decrease the smaller temperature scale, so the Batchelor scale. And in this case, we use a multi-resolution strategy. So we use different grid resolution when we increase the Prandtl number, so that we are able to capture also the smallest temperature scale that became smaller as we increase the Prandtl number. Basically, it goes with the 1 over the square root of the Prandtl number. So this is the setup that we use. So it's a shear Reynolds number 300 for Prandtl numbers from 1 to 8. We can see here also the type of how we define the Prandtl number. That is, in this case, we increase the Prandtl number not by changing the viscosity, which remain constant among the cases, but we decrease the thermal diffusivity, and it is why the Batchelor scale becomes smaller as we increase the Prandtl number. Now, let's take a look first at the slice in the middle of the channel. So we will see that all the drops that are initially in two arrays will migrate to the center of the channel, and they will start to release their heat in the carrier phase. So the carrier phase will become hotter, and at a certain point, since the system is adiabatic, we reach the thermal equilibrium in which the temperature is constant in the entire domain. So this is Prandtl equal to 1, so where the momentum diffusivity has the same order of the thermal diffusivity. We can see here that the drops are initially hot, so they are red, and then we can see also topological changes of the interface, and then at a certain point, we reach the thermal equilibrium, and the entire system becomes blue because it's colder, because we have a high volume fraction for the carrier phase, and we have the thermal equilibrium. We can also see that the scales of the turbulent fields are more or less similar to the scale of the temperature field, and we don't have a big difference between let's say, the drop shape and the temperature scale that we find in the flow. Now we go to Prandtl equal to 8, so we decrease the thermal diffusivity, which means the temperature scale are going to be smaller. And we can clearly see here that we have much smaller temperature scale because the Prandtl number is higher, so the Batchelor scale is smaller. And also we can see that the transient is much, much slower. So while for Prandtl equal to 1, we reach almost immediately the equilibrium temperature, so the two phases have the same temperature. In this case, the time required to reach the thermal equilibrium is much larger, and we can see here that still we are not in the thermal equilibrium, and we can see that we have some streaks inside the drops phase, and it takes much more longer. So this is the end of the simulation, but still this is not the final situation in which we have thermal equilibrium, so blue in the entire system. Now, to quantify this qualitative observation, we compute the mean temperature. So we want to quantify how fast is the heat transfer. We compute the mean temperature inside the drop phase and inside the carrier phase over time. What we obtain is something like this. The dashed line represents the thermal equilibrium temperature, so that depends on the volume fraction. And we can see here that the drop phase initially starts hot, equal to 1, and then the temperature of the drop phase as heat is released from the drop phase to the carrier phase goes down. Likewise, the carrier, as heat is transferred from the drop phase to the carrier phase, became hotter and reached the temperature equilibrium, that is this dashed line here. We can see that as we increase the Prandtl number, you can see here from the video, so we move from top to the bottom, the heat transfer became slower, and so for Prandtl equal to 8, much more time is required to reach the thermal equilibrium situation. Now we're interested in understanding also if the drop size play a role. Indeed, for instance, here we have two different types of events. The first one is a breakage, and the second one is coalescence. So we can see that in the first row, when the drop break and we have the formation of a smaller drop on the bottom part, we can see here that the bottom drop immediately cool down to the ambient temperature, while by opposite, when we have a coalescence, we have the mixing of a cold and say hot drop, and due to this mixing, the mean temperature increases, so the heat transfer can also be modified by the coalescence event. So we now consider the temperature of each drop depending on its size, and we have here 4 time instant, so 1000 and for Prandtl equal to 1, and we move up to the final time, which is 2400, which is almost the final time. And we can see that small drops, so on the left side of so each dot here represents 1 drop. We can see here that small drops immediately reach the equilibrium temperature. So even at time 1050, they are already at the equilibrium temperature. While larger drop, so when we move to the right side of the graph, we can see that drop takes much more time to reach the equilibrium temperature, and so the heat is transferred in a much slower way when the drop is larger, because the drop has a much larger heat capacity, so a lot of heat is stored in the drop, and much more time is required for the drop to release the total amount of heat in the carrier phase. Now, this is Prandtl equal to 1. Let's take a look at the situation at the different Prandtl number, and we can see that for Prandtl equal to 1, the transient is quite fast, while as we increase the Prandtl number, so we move from panel A to B, and then on the bottom row, the dynamic is much slower, and so for the larger Prandtl number, so equal to 8, so the bottom right corner, still at time equal to 2400, we have not reached the thermal equilibrium, and only the small drops are close to the thermal equilibrium, while large drops are still far from the thermal equilibrium. We can also see that the small drop, as we increase the Prandtl number, can go below the equilibrium temperature. Indeed, if the heat is not completely released, the carrier flow is still colder than the equilibrium temperature, and so these drops that are very small, so they takes a very small time to adapt to the environment temperature, can find local spot in which the temperature is lower than the thermal equilibrium temperature, and immediately they adapt to this lower temperature. Then at the end, let's say in the long-term situation, they will all reach the equilibrium temperature. Now, this is how the heat is transferred. So we have characterized the mean temperature variation and the drop size effect on the heat transfer. Let's try now to also analyze the drop dynamics. So how many drops do we have, how large they are, and how many large drops do we have, and how many small drops do we have. Indeed, starting from the two array situation, at the end we have a dispersed flows with drops of different sizes and very different shape. Now let's do first some theoretical consideration. If we have a drop and we have a turbulent fluctuation that could try to deform this drop, we can find an equilibrium situation in which the surface tension has the same, the surface tension forces has the same intensity of the turbulence forces or the turbulent shear forces, and the drop will not break. This is basically the critical situation. And if the turbulence shear forces are larger, the drop will break. Otherwise, the drop will not break. If we do a balance of these forces, we can find the critical situation, which is the Kolmogorov-Inthes critical radius. So this basically distinguishes between the situation in which the drop will break or not, more or less, let's say. Now, depending if our drop is larger than the scale or smaller than the scale, we have different scaling that reflect how the different mechanism that is behind the generation of this bubble. So for small bubbles, so smaller than the Kolmogorov scale, so they are unlikely to break, we have a -3/2 scaling law, while for drop larger, we are in the breakage dominated regime, and the drop size distribution will follow another type of scaling, which is the -10^3 scaling law, because in this case, the cascade of drops is more likely to be generated by the turbulence breakage phenomena, while smaller drops are more likely to be the result of the interaction between small bubbles. Now, this is the two scaling law that we expect from a theoretical consideration. And if we compute our DSD obtained from the simulation, we can see that we are in very well agreement, at least in the breakage regime, for this kind of distribution. So we can try to think of modeling also the drop size distribution with two scaling law, one for the drop above the Kolmogorov-Inthes scale, and one for the drops that are smaller than the Kolmogorov-Inthes regime. Now we have these two ingredients, and we have so the drop size distribution and how the drop size influence the heat transfer. And we want to try to bridge these two elements and find a model that tells us how fast is the heat release in the entire system. So a simplified model that tells us how fast is the heat transfer process. Now we can start from energy balance for an isolated drop, in which the heat transfer coefficient can be obtained from the boundary layer theory, in which also slip has to take into account, because the drop is not a solid object in which no slip condition are applied, but we can have slip at the interface. And by using boundary layer theory, we obtain this thermal energy equation for the single drop. Then we can divide our distribution in different classes, and by integrating among the different classes, so on the drop size distribution, we obtain the mean temperature of our swarm of drops in the turbulent flow. Now let's see how this model, so the integration on the different classes diameter, behave against the DNS results. And we can see here that we have the model predicted, the result predicted by the model with the continuous line, while with the empty dots, we have the DNS results. And we can see that our model is able to predict very well the heat transfer process in the system. We can also see that this line looks very self-similar, so they resemble somehow a kind of self-similarity. And indeed, if you rescale time with the heat transfer coefficient scaling law, depending on the prime number, so prime to the -2/3, we can basically collapse all the line on top of other, which basically tell us that the heat transfer process in this case is self-similar, and so it's more or less self-similar among all the different prime numbers that in this case are super unitary, so they are larger than the prime number equal to 1. So to summarize a bit on this first part on the heat transfer in droplet and turbulence, we studied the influence of the drop size and the prime number on the heat transfer. So as we increase the prime number, the heat transfer became slower. And as we increase the drop size, the heat transfer became also slower, and larger drop takes much more time to release the heat in the carrier phase. We've also been able to develop a model, a phenomenological model, that can tell us how fast is the heat transfer depending on the drop size distribution and on boundary layer theory. We also found via this model a scaling law for time, and we are able to collapse all the curve, all the lines on top of the other. And also we observe that the average temperature and the diameter are of course correlated because larger drops takes much more time to release the heat in the carrier phase. Now let's try to drop some assumption and move to the second part of the talk, which is on modeling of boiling heat transfer with the phase field method. So before we were assuming that there is no phase change, but in most of the applications that we are interested in, like for instance in nuclear energy or in the boiling process in a nuclear reactor, phase change is the relevant phenomena that is used to transfer heat from the fuel rod to the water, in this case, to the carrier flow. So now we want to try to extend the phase field method formulation that we have been using before for two immiscible fluids without phase change to also model phase change phenomena, so boiling heat transfer, condensation, or also melting. Now the problem is again multi-scale, so we have a very strong interaction between phenomena at very different scale. So first, we have nucleation phenomena that are controlled by the atomistic scale of the interface. Then moving to larger scale, we have the microlayer dynamic, which is again controlled by surface tension phenomena, which act at larger scale. And finally, the macroscopic behavior of the bubble is determined by the turbulent flow, and we have much larger scale involved. And again, this isn't a problem because we have a large scale separation that almost cover 8 to 9 orders of magnitude that we need to fully resolve to obtain, let's say, the correct system behavior. Now in this talk, we focus mainly on the on a phase field method for the macroscopic scale, so to describe the interface as we have done before with the turbulent flow. So we are interested in solving the macroscopic hydrodynamic scale from the largest scale to the Kolmogorov scale and down to the Bachelor scale of the thermal field. So we focus, let's say, on the larger scale, and for the moment we neglect, let's say, the microlayer modeling and nucleation phenomena modeling. We again use a phase field method. In this case, it's the conservative Alencane, which is a second order equation because we are going to use a different, let's say, discretization method. The phase field will be equal to 0 in the liquid phase and equal to 1 in the vapor phase. And again, we have a thin transition layer between the two phases. So it's again a phase field method. Just what changes here is the type of equation that we're going to solve because the conservative Alencane gave us some properties that are advantages in this case of boiling phenomena where we have large density ratio between the two phases, between the vapor and the liquid phase. So the first equation that we solve, okay. So first we start to describe the flow field in which we don't have anymore a divergence free flow field in the entire domain, but we need to account for phase change. So the volume expansion that occurs at the interface. So we modify the mass conservation equation, adding an additional term that accounts for the volume expansion of the two phases. And then we have the classical Navier-Stokes equation, in which rho is now a function of the phase field, because the density depends on in which phase we are, if we are in the vapor phase or on the liquid phase. We have the interface advection, which is, in this case, is the conservative Alencane equation, in which beyond the two classical terms, so the diffusion and sharpening term, that this term are used for immiscible phases, so when we don't have phase change, we have an additional term, the last one in red, which accounts for the phase change. So it's basically a source term that accounts for the growth of the one phase, so the vapor phase, at the expenses of the liquid phase. Finally, we have the energy equation, in which we have the free term, let's say the advection and diffusion term that are the classical one, plus the phase change term, because every time we have phase change, we need to account also for the heat exchanged via the latent heat mechanism. So by solving this system of equation, we're able to model boiling heat transfer also in the context of the phase field method. Now we solve this equation. Now first, the main unknown here is the M3 dot, which is the amount of, say, phase A that is transformed in phase B, so the boiling rate. The boiling rate is here computed from from the surface vaporization rate. So we compute first the surface vaporization rate, which is here computed using a heat conduction model. So we evaluate the gradient of temperature on the two sides of the interface. Then, since this is information on a surface, using the gradient phi operator, we transform this quantity from a surface quantity to a volume quantity that we can directly use in our equation, which are evaluated on a volume. The heat flux, so the vaporization rate is here computed with the heat conduction model. So we need to compute the gradient of temperature at the two sides of the interface. And for doing so, we use a probe method. So we have two probes that are separated on the two sides of the interface. And one is used to estimate the temperature gradient on the liquid side, and one is used to estimate the temperature gradient in the vapor side. Usually we can also simplify a bit this model, because every time we have boiling heat transfer, one phase is always at saturation condition, so the gradient of temperature in one phase is always 0. So we can just deploy one probe to estimate the temperature gradient in the phase that is driving the phase change or the boiling in this case. Now we discretize this equation with a finite difference method. We use a staggered approach in which the velocity are defined on the cell faces, while pressure, the phase field, and the temperature are defined in the center of the cell. We use explicit time advancement and a projection correction scheme for the Navier-Stokes equation. And in this case, since we don't solve for u but for rho u, we are able to solve we have a simplified version of the Poisson equation in which only constant coefficients are involved, which is simpler to use, and we can use fast direct Poisson solver to solve this equation rather than using non-constant coefficient schemes that are usually a bit trickier to use in this kind of context. Now let's try to validate our model. So the first case that we consider is the constant vaporization rate. So on the left side, we have the liquid, and heat, a constant heat is supplied from the wall, and vapor is located on the right side. So in this case, since the heat flux is constant, we expect a constant motion of the interface. And in particular, we expect that the liquid will remain motionless, while the vapor will try to move will go out from the outlet located at the right-hand side. And we can also obtain analytic solution for the velocity jump, which in this case depends on the interface displacements, on the amount of the velocity of the interface, which depends on the vaporization rate, which is constant in this case, and on the density ratio. So when the two phases have the same density, there is no velocity difference between the two phases, and it increases as we increase the density ratio. So we can see here that our results of the model, so it's 1D simulation here, are in close agreement with the theoretical values, and we have a perfect match with the definition of the mixture velocity and also of the pressure jump. Again, also for the pressure jump, we can see the vapor recoil pressure, and we have the pressure jump between the liquid and the vapor. Now we move to a more complex, let's say, scenario in which we have a vapor which is superheated. So the wall on the left-hand side is superheated, and the liquid is in saturation condition. Now in this case, it's the vapor that drives the phase change because it's superheated. And this is the Stefan problem, and we can obtain a solution for the movement of the interface. So in this case, the interface will start from the left, so very close to the wall. And as the vapor expands, so liquid is transformed into vapor, the interface will move from left to the right. We have an analytical solution that is basically the interface will move with the square root of time, and the xc parameter can be obtained from the transcendental equation here below. We can see that our results are in perfect agreement with the theoretical relation and also with previous literature works for the entire range of density ratio from a density ratio equal to 1 down to a density ratio equal to 0.001, which is almost vapor and water properties at the standard pressure condition. we can also obtain a solution for the velocity in the liquid, and also in this case, we can see that the velocity in the liquid is in perfect agreement with the theoretical relation. Now we move to a different case. In this case, we just have diffusion in the vapor phase and no motion, and the liquid has a constant velocity, and it's also at saturation condition, so there is no transport of the temperature in the liquid phase. This is the second, let's say, Stefan problem, or also called absorption problem, in which the vapor is at saturation condition, and the liquid, in this case, is superheated. So in this case, it will be the liquid phase that will drive the phase change. And again, the interface will move from the left side to the right side. And in the liquid, since we have diffused, the liquid is not anymore motionless, we have also a boundary layer because we have the diffusion and advection in the liquid phase. Also, for this case, we can obtain an analytical solution starting from the Stefan problem. And also in this case, the interface will move depending on with the square root of time. Now the transcendental equation is a bit more complex, but it's easy to solve with, for instance, with MATLAB to get the psi value. And we can see here that our present results, so in red, are in very good agreement with the theoretical relation and as well with our previous work that has been performed considering this type of problem. We consider here water properties, so the density ratio between the two phases is almost 1,600. Also, for this case, we can obtain the theoretical liquid velocity, and also in this case, we can see that the velocity goes down as time advances because the vaporization rate became smaller as time advances, and so the liquid velocity became also smaller. And also in this case, we have a very good agreement with the theoretical relation and previous analytical and previous numerical simulation, like the WELC in which the volume of fluid has been used. The last case that we consider to validate this type of system, this type of phase field methodology, is a vapor bubble in a superheated liquid, and we prescribe here a constant vaporization rate, so the amount of liquid that is transformed into vapor is constant over time. So let's say it's a simplified version of the Scriven problem. We consider here water properties, so the density ratio is equal to 1,000, and since the vaporization rate is constant, just with from mass conservation, we can obtain an analytical relation for the growth of the bubble over time. So indeed, since the vaporization rate is constant, we expect a linear growth of the radius over time. So the computational domain here is two-dimensional, and we have pressure outlet boundary condition on the sides of the domain, and the vapor bubble is initially located in the center of the field, in the center of the domain, and we have a free outlet boundary condition for the velocity in the four sides of the domain. So we can also see here that for almost all the grid resolution, present results are in very good agreement with the analytical solution. And it's important to observe that here the vaporization rate is pretty high, close to, let's say, experimental setup. So this, let's say, show that the method is consistent, and it's also for this very critical condition, we're able to get a very good agreement with the analytical relation, even though the mass vaporization rate is very high. So it's very challenging from a numerical point of view to model this type of system, and especially because we can have spurious currents. Now, to close and summarize on this part, we have developed a phase field method for boiling heat transfer, which has been validated against a common benchmark. The Stefan problem, the absorption problem, and the growth of a bubble in 2 dimensions, and also we're going to work in 3D. The method is tailored toward large-scale simulation because we have a FFT-based solver that we can efficiently run on many GPUs or on many, can be easily parallelized. We are currently working on the parallelization and porting of the two GPUs of the present code, and extend it to, let's say, more challenging setup for boiling, like film boiling, in which you have a thin layer of film, a thin vapor film that is going to generate the boiling, and we have a derailleur instability on top of that. and also modeling of wetting phenomena, so different contact angle between the drop, the vapor bubble, and the substrate. Finally, I would like to thank the collaborators that has been co-involved in this work. So Professor Soldati from TU Wien, Matteo from MIT, and Francesco and Francesca for the work on the heat transfer in droplet and turbulence. And with this, I would like to conclude to thank you for your time and open for any question.
Great. Well, thanks so much, Alessio, for the very nice talk. And yeah, we have time for questions. So I know I think a couple people have indicated that they had questions. So maybe please feel free to unmute and ask your question.
One second, I have to let them.
Oh, sure.
Okay, now I think they can. I think they can unmute now.
So hello, I was the second one, I guess, that was interested to asking questions. Do you hear me, by the way?
Yeah.
Yeah, okay, great. So Alessio, thank you very much for interesting presentation. My name is Tomasz Wacławczyk from Warsaw University of Technology. I would like to ask a general question about your phase field modeling. What is the main difference between the phase field model you have shown in the first part and the second part? In particular, my question concerns the difference in chemical potentials that you have introduced. So let's say this is the first part of this question. Can you comment on that?
I lost you for a while.
So one more time, my question is about the differences in definitions of the phase field methods you are using in the first part of your presentation and the second part of the presentation. What is the main difference between them, in your opinion, in particular, when you are looking at the chemical potential definition?
Yeah, so the first one, which is based on Canadian equation, is basically a thermodynamical based phase field method in which you have the chemical potential that basically at the right hand side that control, let's say, is the balance which is come from a Ginsburg-Landau energy potential. So it's, let's say, that one control the phase separation, let's say, but it's, let's say, with a pseudospectral method, it's not too bad to handle it, but sometimes it gives you some drawback, like some like small drops can disappear because the chemical potential want to, let's say, to minimize the total energy by removing, let's say, this small drop that have a very high surface to volume ratio, and it likes, let's say, the Ginsburg-Landau tries to minimize the energy, and this is a way in which it minimizes the energy. The second one is not anymore thermodynamically based, but let's say it's based on just geometrical reconstruction. It is the conservative Lenkan. And in that one, it's very close to a conservative level set method in which you're basically transporting the tangent profile of the interface, and there is no thermodynamic involved there. It's just a transport equation for the hyperbolic tangent profile. So there is, from my point of view, there is no thermodynamic there, and it's just it's very similar to volume of fluid or more. It's very close to a level set in this case.
To which level set? This that is using, say, distance function, or
no, the conservative level set in which you have the transport of a hyperbolic sine or hyperbolic tangent profile.
And can you maybe go to the slide where you have the equations of this second phase field method?
Yes. Oh, wait, sorry. Wait, sorry, here I have a double slide, but here.
All right, so you are using only one field of this sigmoidal function, right? Here, you don't use any switching between this and the sine distance function to compute normal vectors, for instance.
No, it's just yeah. This is the, let's say, the first version in which you don't have phi and psi. You can also improve it with the accurate conservative diffuse interface in which you have in which the sharpening term is computed with a different approach. So you compute first the distance function and then you use it to compute the sharpening term.
Okay, so maybe only as a comment for you, there is a relation between this equation and the Ginzburg-Landau functional. In fact, the right-hand side of this equation is simply a functional derivative of the modified Ginzburg-Landau functional that contains curvature effects, and it is published in some of the papers in the literature. So you can read about that. If you would like to. Yeah. Also, this equation provides a very nice link between all the definitions of the models of the interface we know. It shows how the sharp and diffuse interface models are related, and provides the definition of the order parameter too, and the definition of this what sharp interface is. All right. So I should encourage you to read a little bit more about this, and if you would like to, I can provide literature if you would like.
No, I know your work. I remember I read it because I did it. But
okay.
Thank you.
So anyhow, thank you for a nice presentation and your answer. Yeah.
Great. Other questions?
Andrea, I think there is Roman and Fabio on the chat. Otherwise, I'll have a quick question for Alessio while we wait for the others.
Okay.
Alessio, in the problem of droplet cooling, do you stabilize the droplet size distribution before you start the cooling process, or the transient start at the same time? So essentially, what I'm asking is whether you have obviously two time scales. One is the hydrodynamic scale to reach the distribution equilibrium, and the other one is the cooling. So I wasn't clear from the presentation whether you were, first developing the distribution and then cooling, or cooling and developing the distribution of bubbles at once.
Yeah, we are the two, let's say, time scale. So the two phenomena are superposed. So we have, let's say you start from the array, and the array start to cool down at the same time the swarm start to interact with the background flow. So the two, let's say, phenomena are superposed. This can be only an issue with, let's say, parameter equal to 1, while for the other case, since the heat transfer is kind of slow compared to the hydrodynamic scale, you reach more or less the equilibrium in terms of drop size before the heat is totally transferred to the carrier phase.
Okay, well, thank you very much.
Thank you.
All right. Yes, maybe Roman and then Fabio, if you both have questions, we can go in that order.
Yeah, thank you. Fantastic talk, by the way. I appreciate it. It was awesome. I have a question regarding the basically your mesh setup and how you set up your interface between the two components, like the liquid and the vapor, and how you said you transformed that basically that area interface into a volumetric interface. Like, can you explain a little bit more how you did that, how you justified doing that, and like, I guess how you implemented that?
Okay. That's, let's say, still a bit of open challenge, especially in 3D, because you basically need to evaluate, let me here. So going from, let's say, M2 dot to M3 dot from a mathematical point of view, let's say from a numerical point of view, it's not a big issue.
Yeah.
Because you just have this quantity that is defined on the surface, and then you apply the gradient of phi, and then it becomes immediately volume rate. The point is that computing M2 dots, let's say, because you need to compute it at the interface, and then let's say propagate this information normal to the interface. And yeah, this is kind of still some work in progress, especially in 2D and 3D, because you need to evaluate something in a certain point of the domain, and then spread this information along the direction. So that's maybe a bit challenging, especially if you consider that you are in, let's say, from a parallel point of view, in which maybe your point of the interface is not in the same pencil of the domain. So yeah, that's gonna be a bit challenging, let's say, to parallelize, but I think more or less you don't, since the transition layer is kind of thin, shouldn't be a big issue, because in the worst case, let's say you just do communication between two pencils that are one close to the other, so it shouldn't be.
So for the mesh that you had on the other slide,
Mhm.
like 2 slides back or a slide back.
Yeah, so you basically have some grid points. Some grid point, let's say, will fall between the phi equal to 0.5,
Yeah.
and you need to apply these M3 dots on a few points across this interfacial layer. So let's say you have the phi point equal to 0.5, then you have to apply this kind of M3 dot on 4 to 5 points across the stencil.
So
So you
what
have
is
to-
like, how did you determine the actual length scale that you were going to use for like that?
Yeah, that's epsilon. Epsilon will tell you how thick is this layer in which you're going to redistribute the vaporization rate.
Okay. And that's related to the actual transport of
Yeah.
energy. Okay. Okay.
So it's basically how, let's say, how thick is the interface, if you want to say, let's say in very rough term, is how thick is the interface. Thicker is the interface, larger is the number of points in which you distribute this kind of mass flux.
And have you varied that at all and seen like if your outputs like change dramatically?
No, it doesn't change too dramatically, because it's still a parameter connected to the phase field. So you increase your interface and you also increase this mass flux. So there is a kind of scaling law that you can follow
Oh, okay.
to ensure that
Okay.
it is consistent between the mass flux and the other thing.
Excellent. Thank you.
Thank you. Thank you for your feedback.
I think we have maybe just 1 or 2 minutes left. Fabio, did you want to ask your question? I think you're muted.
Yeah. Hi, Alessio.
Hi.
Thank you for the presentation. I just want to ask, when you define the boundary conditions on the surface, do you use the same values for, do you use the same boundaries condition for the drops and the bubbles?
There is no actual boundary condition on the surface. It's just that the solution, because at the surface, you need to impose the continuity of the viscous term, and continuity is already implemented by the Navier-Stokes equation. So you don't have to impose any boundary condition on the, you use basically source term in the Navier-Stokes equation to satisfy a boundary condition on the surface.
Okay.
So you
Thank
modify your Navier-Stokes equation in order to satisfy your boundary condition at the surface.
Okay, thanks.
It's similar to the immersed boundary method, in which you apply some forces to satisfy the no-slip condition on the solid sphere or solid object that you have in the domain.
Do we have time for just one more question? I'm sorry.
Yeah.
So I know you said in your future work you're going to be looking at film boiling. So basically, like this is all applied to like post CHF. Like I'm assuming that the film boiling will be applied to post CHF and basically heat transfer coefficient degradation and how it's transported in between the superheated vapor, subcooled liquid, or in the case of DMB where you have superheated, you may have superheated droplets, or you may have superheated bubbles and then subcooled liquid and stuff like that. So where do you see the film flow boiling? Like, are you going to take a similar approach with the interface technique? And if so, how much do you think that the large temperature gradient that you're going to see compared to like what you're seeing here is going to impact the results.
Of course. So the large temperature gradient will have an effect in the sense that you will need a much more grid resolution. That's not always, let's say, that's more or less fine because it's not far from the Kolmogorov scale, so it's fine. The other problem is that most of the people doing numerics do the film boiling case because you don't need to model the nucleation part, which occurs at much smaller scale. So either you start from, let's say, from a seed, that is your, and then the bubble will grow from your seed, or if you need to model nucleation events, then you need some kind of multi-scale approach in which maybe like some grid models basically that tell you, yeah, I will nucleate a bubble here just based on some other assumption, or like starting from fluctuating dynamics or something else. You go there and let's say you create your own bubble, your seed, and then this will grow. So this is why the film boiling, let's say, benchmark is kind of well established in the numerical part because you don't need to nucleate anything. You have a film there, and you start to grow this film. Let's say this film will start to grow and see this kind of mushroom shape. Usually, you find. Let's say this is avoid to model the micro layer part and also large temperature gradient and interface and also the nucleation part. Yeah, you avoid, let's say, to go into the multi-scale, the very strong multi-scale part of the problem, and try to, let's say, have a simpler setup that you can test at play at the beginning.
Excellent. Thank you. I may reach out to you personally just to ask a couple more questions if you don't mind.
Yeah, sure. I will be
Awesome.
there next week, so in 2 weeks.
Oh, cool. Well, then maybe we'll just have a chat over coffee.
Yeah, sure.
All right, great. Well, with that, thank you again, Alessio, for the really nice talk, and thanks to all the audience members for the great questions and discussion. And I think we'll wrap up here then.